All right. In this example, we have a group of 5 people selected at random. What is the probability that at least 2 of them have the same birthday? Okay. Now we're going to make some assumptions. We're going to assume that none of the 5 people was born on February 29th. Okay. So we're going to eliminate that from our possible birthdays. Basically, so we can work with just the 365 days in a year. And then we're also going to assume that each person is equally likely to have any of the 365 days of a year as his or her birthday. Okay, so we're going to make those assumptions. All right, well, so let's think about how we could do this problem. The key to solving this problem is to recognize that the complement, right, the opposite of what we want, the complement of at least 2 people sharing a birthday is none of them share a birthday. Okay, so essentially we can think of it at least one pair of people share a birthday. So then you kind of can see it as at least one pair of people share a birthday is the opposite of none of the people share a birthday. All right, so we're going to actually figure out the probability of the complement, the probability that none of them have the same birthday, instead of what we want to count directly, and then use complementary counting. All right, so we're going to find the probability of the complement of what we want, which is 5 different birthdays. Okay, so we want to know what's the probability that these 5 people all have 5 different birthdays. Okay. And as you would guess, let's say, there's 365 days in a year, and you only have 5 people, so you would guess is a fairly low probability, or fairly actually high probability that they're all going to have different birthdays. Okay, which then means that there's a pretty low probability that 2 of them would share a birthday. But let's go ahead and think this through. So. All right, so how many ways so our numerator is the number of ways that this event can happen, right? The number of ways that people could have 5 different birthdays, right? So if we think about the first person, how many possible birthdays could they have? They could have any of 365 different birthdays, all right? The next person, now we don't want them to have the same birthday as the person before, right? Because we're only counting the event where they have 5 different birthdays, and we want to know how many ways that could happen. So that means that the second person has to have a birthday that's not the same as the other person. So there's only 364 days left for that person, if they have to have a different birthday. Okay, then the third person then would only have 363 different birthdays possible, and then 362 for the fourth person, and then finally the fifth person would be 361 days. Okay, so we want them to all have different birthdays. So those are essentially, if they could choose their birthday, the number of ways that could happen, right? It was just basically a permutation of 365, and we're choosing 5. All right, now that's the number of ways they could have 5 different birthdays, but we want the probability, so what we need in the denominator is the total number of ways that their birthdays could fall without any restrictions. So they might have the same birthday, they might not have to have the same birthdays, right? So the first person, they can have any one of 365 birthdays. And the second person could also have any of 365 birthdays. And the third person, the same thing. They have 365 possible birthdays, and so on, right? So all 5 people have 365 possible birthdays, right? So it's just basically 365 to the 5th power. Put that in your calculator now, and what you get is 0.9729. Okay, so about a 97.3% chance that they are going to have all different birthdays, which makes sense, right? So what's the probability then of the opposite of this, right? What we want, though, is to figure out what's the probability that at least two of them share a birthday. So, so let's write that down. At least two share a birthday. Okay, or at least one pair of people share a birthday. So that's the opposite. So we're going to use complementary counting. I'm just going to take 1 and subtract the opposite of what we want. And that's 0.9729, which tells us that 0.0271, so about 2.71% chance that there will be at least two people who share a birthday. So that's fairly low. That's not very likely. Not very likely. Okay. All right. Well, that doesn't seem too remarkable. That seems like what we would expect. All right. But this is actually a famous problem because it does give an unexpected result. It gives an unexpected result when you have a higher number of people. Here we only had 5 people. I chose 5 people because 5 people is easy to calculate. It gets a little more difficult when you've got more than 5 people. Okay, you get a lot of numbers. So here we only had to multiply 5 numbers together. Permutation of 365 things taken 5 at a time. But if we selected 30 people, then we'd have a different story. But let's take a look at what happens if we were to select 30 people. Right? If we had a group of 30 people, let's calculate the same probability. We want the probability that at least 2 share a birthday. So I'm going to calculate the probability that of the opposite of what I want, which is 30 different birthdays. Okay, so that's the opposite of what I want. So this is the case where nobody shares a birthday. So essentially I get the permutation of 365 things taken 30 at a time. Okay, it's the first person has 365 possible birthdays, and then next person has 364, 363, 362. Right? It's a big long calculation, and we're going to divide this now by 365 to the 30th power, because the total number of ways that their birthdays could fall would be 365 possible birthdays for the first person, 365 for the second and third and fourth. So basically everybody has 365 possible birthdays. So this is an ugly calculation. All right. It really is only possible on your calculator up to a certain point. Otherwise you have to use a computer to calculate it. So, but if I think this one you can actually put into your calculator. I don't know that you can calculate it directly by multiplying everything out, but if you put the permutation of 365 things taken 30 at a time and divide by 365 to the 30th, at least on my calculator, I think I got this to work. I get 29.37%, or 0.2937. That's my probability that they would all have different birthdays. So what I want, though, is to figure out how many, or what's the probability that at least 2 of them share a birthday. At least 2 share a birthday. Okay. Or one pair of people. All right, so we're just going to take 1 minus that, right, because it's the opposite. And what I end up getting is that there's 0.7063. So about a 70% chance, over a 70% chance that if you have 30 people in a room, that there will be one pair of people that share a birthday. So this is actually very likely that this will occur, which that is a little surprising, right? Because it seems like, if you think about, well, there's you get only 30 people in a room, you got 365 possible birthdays. It doesn't seem like it should be that high. But if you think about the number of pairs of people that you have, because you could pair people up in any way, right? I mean, you think about all of the pairs. Like, how many ways can I take 30 people and choose a pair of people? It turns out to be like 435 people. And if you think about it that way, then you see that, okay, then maybe it's more likely, because now we're just trying to find at least one one pair that shares a birthday, and we've got actually 435 pairs of people. Okay, so let's take a look at this problem is actually in your book, and there's a table in your book that actually gives the probabilities for various groups of various sizes of groups of people. So the R is the size of the group, right? And then they've calculated the probability. So this was the 5 that we started out with. 30 is right here, so that's the other number we calculated. But what's interesting too, you only have 50 people in a room, and there's a 97% chance that some pair of people will share a birthday. All right. So there you go, the birthday problem. I'm going to put a couple of links in the hyperlinked lecture notes. As optional videos you can watch. It might be more interesting than my videos. I don't know. Just on this problem. All right. Well, that's all I have for you in the lecture portion of this section, and so you are ready to start the discussion questions, and I'll see you in class.